last week we concluded that the mean velocity, the mean flow velocity is equal to the discharge and divided the total cross section area. Okay, so and we pick up two conditions. The first condition is the pipe flow. Okay, so and the second, usually we call that the channel flow. Okay, the channel flow is very famous. It is similar to the condition of the river channel flow. And the pipe flow usually we see in the house. Okay, so if you understand the condition of the pipe flow, and then we will see the ratio between the mean velocity and the V maxima is the 0.5. Okay. In other case, if we see the channel flow, and then you see the ratio between the mean velocity and the V maxima is 3/2. Okay, and the final one is also we keep the pipe flow, but the flow condition change to the turbulent, and then you see we don't have the certain ratio values because it's based on the turbulent flow. We don't know the flow condition of the turbulent flow. So you see their ratios, there is a ratio, but we have no certain values in here. So the key knowledge in here, if we are talking about the mean velocity, if we have the discharge and we have the total cross-section area, and then we can compute the V mean velocities. Okay, so we divided the two conditions. We have the open channel flow, like the rectangular shape, and we have the pipe flow. So we would like to know why the reasons the V means for the open channel flow is always equal to 3/2 V maxima. This is for the channel flow. And the second, if we consider the flow condition is pipe flow, so there is always relationship between the V means and the V maxima is 0.5. This is for the pipe flow. So we wondering to know why we can conclude that the result showing here. Okay, so we need to base on the initial concept. We always know the Q is equal to integrations the V dot dA. Okay, this is the general formulas for the discharge. If we can compute the discharge and then we know the total area of the cross sections, based on two parameters, we can calculate the mean flow velocity is derived by Q divided the total area. Okay, so the basic idea we need to from here, the Q, the definition of the Q, and the Q is discharge. Okay, so if you take a look, the two conditions only difference is the dA. The dA, we have the different dA values if you consider different flow conditions. So totally we only have the 1 and 2 is a pipe flow and the channel flow, and then you see how difference in dA values. Okay, so we step by step. First we consider the channel flow. So this is the channel, and you see there is Y. Usually because this is the channel, so the Y always we call that is the water depth. Okay, because different condition we have a different water depth in the river channels. Okay, and for the one curve sections, we have the width. We have the width of the river channels. So the key knowledge in here, because we need to define the dA first. If we have the dA, and we can define the Q, because we actually know the flow field, velocity field, and the dA, and we have the Q. But here I don't use the dot product because we assume this layer is the flow directions is always parallel to the normal factor of the cross-section area. So here I don't use the dot product here because they are always parallel in the same directions. And then if we know the dA, so you see what is dA? dA is the small cross-section area. So the width is always constant. The width is always constant, and we have the small water depth changes. So there is the dy. Okay, so dA is the width multiply small change along the water depth. So this is the cross-section area, but it's just one piece, small. dA can be represented by width multiply dy. Okay, and what is the velocity field? The problem already provides you the velocity field. So I write down in here, and then you see the flow velocity is a function of the water depth. And if you take a look, this is 2 times y divided h minus y squared divided h squared multiply the V maxima. So what is h? H is the total water depth. H is the total water depth. Okay, so in that way, you know based on this formula, if y is equal to 0, that means your location is located at the bottom of the channel, right? And you put the y equal to 0 into these formulas, you know the velocity is equal 0. That means in the channel flow, the flow velocity at the bottom is equal to 0. It makes sense, right? Because there are large shear stress at the bottoms. So you can try to image that at the surface, water will have the highest flow velocity. At the water surface, will have the highest flow velocity. So based on this idea, we have the dA and we have the V velocity field. So we can calculate how much discharge we have in these systems. So we do the integration problems in here, and I put the V velocity. The V is 2 times y divided h minus y squared divided h squared. And we have the V maxima, and there is a dA, right? So dA, I write down in here, this is W dy. And based on these integrations, you know your interval of the integration is along the y directions. So the interval is start from 0 to the total water depth is equal to h. So you can try to solve these integration problems. So I just move some constant value outside. So first is V maxima is always constant, and the width didn't change with the y directions. So I move the width outside. So inside we only have the the v velocity is 2 times y divided h minus y squared h squared dy. So simply we just integrate these functions of the y. So we have a v maxima again and w, and we do the integration here is y squared divided h minus 3 times h squared over y cubic. Okay, and then the integration interval is start from 0 to h. So simply way you don't need to consider the 0 condition because you put the 0 inside, there are no nothings. So we only consider the h. So finally, you know the v maxima multiply width, and I put the h inside. You know there is h minus 3 over h. Okay, if you put the h inside, so finally you can summarize the equation is 3 over 2h, and multiply there is the width, and there is the v maxima. Okay, but we wondering to prove the formula showing here. So based on the definitions of the mean flow velocity is equal to q divided a. Right now we already have the q value here, right? Q values. So what we didn't know is a in here. So we calculate the a first. So what is the a? A is the total cross-section area. Since we know we have the total water depth h, and we have the width here. So the total cross-section area is total water depth multiply the width. Okay, so right now we have the a and we have the q, so we can compute the mean flow velocity is 3 over 2h width and the v maxima divided the total cross-section area in here. So you can cancel out the hw, right? So finally we only have 3 over 2 v maxima, and we prove the formula showing here. Okay, so if you don't remember or you forgot total anything for these formulas, you can derive this formula by yourself, right? You just based on, you know the q and then you know the a, and then you follow these definitions here, so you know how to calculate the v mean velocity. Okay, but right now I tell you, if you can remember and keep in mind, for the channel open water flow, always follow this relationship between the mean flow velocity and the v maxima. If your problem is the channel flow, but this is based on the flow conditions, always ideal flow, because there is no rotational, and we assume the ideal flow is based on the flow condition is incompressible, right? Okay, and inviscid. So and there is no rotational flow. Okay, so similar way, if we consider the pipe flow, so the difference in pipe flow, you see that we assume the total radial length in here is the capital R. Okay, and you see the pipe flow is a ring. If we consider the dA is the ring area, and then you see because the dA for these ring circles, if we know the total radial length, the circle length is 2 pi r, right? It's the length of the circles. And then we multiply a small radial change, So we multiply the small radial change. That means the changes of the ring width. So the cross-section area of the ring is 2 pi r is the circle length. Sorry, here is a dr. The circle length multiply a small change along the radius directions. So we have the dA value here. And then we have the VR. In the pipe flow, the flow velocity is a function of the radial length changes. So we have the VR is 1 minus r squared, capital R squared, and we still have the V maxima. So in this flow condition, if you have the R, you consider the R is 0. Where is the R is equal to 0? It means the center of the pipe, right? So if we put the R equal to 0 inside these functions, and then you will have the V is equal to V maxima, right? That means along the center of the pipe always has the highest flow velocity. And it also makes sense because if you pick out the point along the pipe boundary, but the pipe boundary have a large friction, right? So along the pipe boundary there is no any flow velocity, but in the center of the pipe they are always the highest flow velocity. Okay, so the similar idea, so we define the Q is equal to V and dA, right? And we actually know the flow functions in here. So we have the 1 minus r squared and the capital R squared, and we have the V maxima, but the dA is in here. We have the 2 pi r is the circle length, and multiply the dr in here. Because these integrations we along the radius direction, so the interval of the integration is start from 0 to capital R in here. Okay, again we just move some constant value outside is V maxima, and also there is a 2 pi. 2 pi is always constant. So inside I only have the 1 minus r squared, capital R squared, and there is R and the dr. And we have the interval start from 0 to capital R. So we do the integrations, very simple. So this is equal to, because the R integrate to become the 2 over R squared minus, and here I put the R inside, so there is a R cubic. So there will be the, after you do the integrations, okay, there will be the R 4 powers, okay, and then the integration is from 0 to capital R. And then, again, you just put the 0, nothing inside. So we just focus on the capital R and put inside. So there is a V maxima 2 pi, and there's 2 over R squared minus 4 R squared, right? Okay, so in following, you just summarize the equation here, and finally you can, this is 4 over 2 minus 4 over 1. So inside is, for this part, is 4 over R squared, right? And they just multiply together. So finally you only have 2 pi R squared multiply V maxima, okay? And then the total areas of the pipe, the cross-section area is also equal to the pi R squared, right? because the r is the radius. So the area of the circle is pi r squared. So go back to our target in here is the mean flow velocity. So it just divided the Q divided by the cross-section areas. So finally you know your answer is equal to 2 over V maxima. And again, you prove the formula shown here. Okay, so again, you just keep in mind this is the always flow velocities is always follow these formulas. If you consider your flow is pipe flow, so it's the half of the V maxima is equal to mean flow velocity. Okay, so if you can remember the two conditions for the channel flow and the pipe flow, so the table just summarize Q discharge is equal to mean flow velocity multiply the total cross-section area. That's why we don't need to consider more complicated formula in here. If you directly know the mean flow velocity, and then you can compute the discharge very quickly. But this is based on the idea the flow directions is always parallel to the vertical normal factors of the cross-section area. If not, you need to use the dot product operator to calculate the discharge. Okay, and usually we have this condition is because the flow is not the uniform flow, so the V in here is always a function of the spatial. So if the spatial changes and your flow condition will changes. If you are the uniform flow, and then you can simply just multiply the V bar, multiply the total cross-section areas. Okay, so if you know the Q values, the Q multiply the fluid densities, and then you have the mass flow rate. The mass flow rate. Okay, so the unit of the Q is the meter cubic per second. So what is the mass flow rate? The mass flow rate usually the unit is kg per second. Okay, so you follow the definition for the mass flow rate is equal to rho Q, right? And the unit of the rho is kg per meter cubic, and the Q, the unit for the Q is meters cubic per second. Okay, so you can double check the dimensionals. If you multiply rho by Q, so the dimensions finally only have the kg per second. Okay, so you need to keep in mind if you compute the Q values and simply multiply the densities, and we call that is the mass flow rate, is a m dot in here. Okay, so you need to keep in mind. So that means you have the Q and multiply the flow density, and then you have the mass flow rate in here. Okay, so we wanted to keep in mind all of the above mentioned ideas. So we just following exercise. You can see, you take a look. This is the condition we have the pipe flow, right? So the condition, this is the pipe flow. And then we know that the fluid right now is the air. So we have the air, and we tell you the density of the air is equal to 1.24 kilograms per meter cubic. Okay, and then I tell you the diameters of the pipe is 30 cms, and it will be equal to 0.3 meters. And I also tell you the mass flow rate in here, the m dot. The mass flow rate in here is 3 kg per seconds. Okay, so I wondering know that what is the mean velocities and what is the discharge. So the mean velocity in here we didn't know, and we also didn't know the Q value in here. So if you remember the formula I tell you before, the Q, if multiply the fluid density, right, should be equal to the mass flow rate. Okay, so it's a very simple, very easy. How can you compute the Q? If you have the mass flow rate, simply way you divided the rho and then you have the Q. Okay, so you check where is the mass flow in here. We have the 3 kg per seconds, and divided the rho is 1.24. So we divided 1.24 over 1, and the unit is meter cubic divided the kg. Okay, and you balance the units, kg cancel out, and finally you can divide the 3 by 1.24 in here, and the unit is cubic meters per second. This is always we call that discharge. Okay, so you calculate by your calculators, the answer is around 2.42 meter cubic per second. So we have the discharge first. Okay, so you have the discharge, and then I tell you the mean flow velocity is equal to Q divided the total cross-section area, right? And following this formula, you didn't know the A, so we can compute the A first. And this is the pipe flow, so we know the cross-section area is the circle. And the question tell you the diameter in here is equal to 0.3. So we have the diameter, so the total cross-section area is 4 over pi d squared. Okay, so you can compute the cross-section area. The d is 0.3 squared. Okay, so you can compute the cross-section area is 0.3 multiplied pi and divided the 4. So it's around the 0.7. Oh, sorry, 0.0706 meters squared. Okay, so since we have the Q is 2.42, and the unit is meter cubic per second, divided the total cross-section area. So I divided 0.0706 over 1, and the unit is the meter over 1. So you can compute the answers by your calculators. Okay, it's around 34.2, because this cancel out the meter square. There is only have the meter, so the unit is a meter per second. Okay, so we just the idea is because why we can follow all of the formula showing here, because we assume the flow directions is always parallel to the normal factors of the cross-section areas. That's why we can follow this formula. If not, we need to use the dot product operator to calculate the discharge. Okay, so this is a very basic idea. How can we compute the discharge, and how can we compute the flow velocities average? Okay, but this is another exercise, because the exercise just tell you please apply the dot product. That means the flow conditions in here, the flow condition in here is not parallel to the cross sections. Where is the cross section? There is your cross section, right? Along this direction is your cross section of the channel. But right now the channel is inclined. Okay, so what is your cross section perpendicular to the flow directions? So should be along this direction, right? If this is the, I write down some image in here. This is the cross section perpendicular to the flow directions. But right now, initially, the cross section is along these directions. So we need to project to this direction, right? So that's why we need to use the dot product in here. So again, this is 30 centimeters is the water depth. So we have the water depth. Usually we call the water depth is D. So we know the D is the 60 centimeters, and which convert to the meter unit. Okay, and then in here, the question would like to you to tell the discharge per meters of the width. The discharge per meters of the width. That means we define the Q, right? What is the per meter of the width? That means the discharge divided the width, and we usually call that is the small q, and you can call that is the flux. Okay, so the only difference compare the small q with the capital Q, we divided the channel width. Why? Because usually we know that this is the river, and the river maybe the width will change a lot, right? Because this is a width 1, and this is a width 2, and this is another width 3. But we know that the different cross-section area along the river channel, the width is totally different, and will change a lot. So if we know, we assume the flux along the river, small q is always constant. The small q is always constant along the river channel. So at the different cross sections, we simply just q multiply the width 1, and then we understand how large discharge in here. Again, in here, how large of the discharge along the width 3, because we know the small q, and simply just multiply the width of the cross-section area along the 3, and then we can compute the discharge very quickly. So usually for the hydrologists, engineers, they always use the small q, don't use the capital Q, because the different cross-section area, the q will change, the discharge will change a lot, because we have a different width. So in here, the questions require you answer how large it is for the discharge per meter of the width. Okay, but the idea, again, we still need to know the Q values first. Okay, so along this direction, we know the area. What is the area? The area is the depth multiply the width, right? The depth multiply the width of the channels. But right now, what we want the cross section along these directions. So we do the projections. So our final total area cross-section area perpendicular to the flow direction is equal to d multiply width multiply cosine theta. And the theta angle in here is the 30. And this again, there is the 30. The theta is the same. So we do the cosine 30 degrees to project the cross-section area to along these directions. Okay, so we know the Q. So we also know what is the velocity. The velocity, the question tell you the velocity always the constant values. So we have the velocity always the constant, the 12 meters per second. What is the physical meaning? This means the flow is uniform flow, right? Because the flow always constant values. Okay, so very simple idea. We just calculate the discharge by the velocity multiplied by the total areas. And the velocity in here is the 12 meters per second. And the area is the d. What is the d? D is 0.6 meters. And what is the w? The question didn't tell you the w. And I assume the width is 1 meter because we are consider the situation is per meter of the width. So I assume the width is 1 meter. So multiply the width 1 meter and do the cosine theta. Okay, the cosine theta is 30 degrees. Okay, so you can compute the answers for this is roughly equal to the 6.24 and the meter 3 times meter. So we have the meter cubic per second. Okay, you can compute it by yourself, but there is not the true answer we want because we want the discharge per meter of the width. So as we know, the Q is divided by the Q divided the W, and we assume the W is 1 meter already. So finally, the number is the same, but the unit changed to the meter square per seconds. So this is our final answers. Okay, so in here the idea is I just introduced another parameters, small q. It's usually we use in the hydraulic problems. So this is just simply you have the discharge and divided the width, and then this is a small q. Okay, so another questions. This is the exercise just require you apply the integrations operators. So what is the flow conditions? If you take a look, this is the flow. We call that is the channel, right? This is similar to the channel flow. And if you observe the curve in here is the flow velocity functions. So we know at the bottom the u is 0, right? Because there is no any flow velocities. But if the water depth increase, we know that the flow will increase when the water depth increase, right? So that's why the curve showing here. Okay, and this is the flow conditions. We always see that the flow directions is parallel to the normal factors of the cross-section area. Okay, so for this problem, we don't need to use the dot product because they are always parallel. Okay, so the idea is what is the discharge in the channel flow? So we need to answer the Q value, right? But as we know that the Q value can be divided by the U velocity multiplied dA, right? And there I don't use the dot. I don't use the dot because the flow directions is always parallel to the normal vectors of the cross-section area, right? But if you remember, I tell you the U mean values for the channel flow is always equal to 3/2 U maxima, right? I tell you because we proved in the previous slide. If your channel, you consider your condition is channel flow. So, and I also tell you, if you know the U mean values, you simply just multiply the total cross-section area, and then you can compute the discharge very quickly. So, even though the question tell me you need to process the questions by integration operator, but I already know that the U mean value is equal to the 3/2 U maxima, right? And if we know that, we have the mean velocities, multiply the total area, and then we can answer the questions because we can calculate the discharge very quickly. Okay, so following the questions, what do we have? The question tells me the water depth is equal to 2 meters. Okay, so we have the water depth here is the 2 meters, and the channel width is 5 meters. And then I tell you the U maxima, the flow maxima velocity is 3 meters per second. Okay, so what is the mean flow velocity? We have the formula showing here. So 3/2 multiply the U maxima in here is 3. So what is the mean flow velocity is 2 meters per second. And then we have the total area, right? Because I tell you the total depth waters is 2 meters, and then you multiply the width of the channel, and this is equal to 10 meters squared. Okay, so I can compute the discharge very quickly because I already know the mean velocity is 2 meters per second, and then multiply the total area is 10 meters squared, and they will equal to 20 meter cubic per second, and finish the answers. Okay, we already answered the questions. Okay, if you didn't know the formula showing here first, you need to do integration, right? If you do the integration again, you still can calculate the Q values. But since we already know the formula in here, so we can solve this problem very quickly. Okay, so that's why I tell you you need to keep in mind some relationship. If under the channel flow, and you see the channel flow, and then you know the U mean is equal to 3/2 U maxima. If the pipe flow is U mean is equal to half U maxima. Okay, and we always know that the Q can be divided by the U mean multiply the total area. If you have the Q, and you can define the mass flow is the rho multiply the Q, and the unit is here is kg per second and the meter cubic per second. Okay, so that's the idea you need to always keep in mind. But this is based on the flow is ideal flow, and the flow directions is always parallel to a normal factor of the cross-section area. If not, you need to follow the formula showing here. The flow field velocity factors multiply the area factors. You need to use the dot per dot. Okay, this is very general formulas when we calculate the discharge. Okay. So the next chapter we will teach you on Friday. So right now we would like to introduce two tools. So we have the tools. The first one is under the curl systems. Another, you just pick up the control volumes. And the two systems we wondering to apply to analyze the fluid particle motions. But we based on the different systems. So one is a curl system, another is control volume. And on Friday, I will introduce more details. But in next, we are trying to analyze the fluid particle motions, and based on the curl systems, another is the control volume systems. And I will tell you the certain definitions. Okay, so today we start here. Okay.